Hello, everyone. So we're going to continue today on talking about fundamentals of logic. So it turns out that whenever we want to represent how a computer thinks about mathematics, we need to think about the logic. So logic comes in many forms, and what we want to do in this section is first of all introduce what is the concept of logic. What does it mean when we talk about logic? What are the representations of logic? So jumping ahead a little bit, I can tell you that whenever we talk about anything in logic, we are always referring to either a true value or a false value. So we're going to talk about how that plays into the whole language of a computer. We're going to talk a little bit about logical connectives. So it turns out that whenever we have different variables in logic, that we can combine them into a connective form, a logical connective form, and we can represent them using truth tables. And in fact, a lot of the logical connectives that we're going to talk about in this course are defined by their truth tables, and we'll talk a little bit about what those are. And then we're going to get into some laws of logic. So given that there's some connectives that we're going to deal with in this course, there's some laws that we can think about that we can apply to these logical expressions. So we're talking about what logical equivalence means using the laws of logic. Now, in the next week, in the next subsection, I guess we're going to also touch on rules of inference, which is another way that we can reason with a computer. So this is the logical laws in the form of implications. So again, if you've never heard of implications, it's okay. We're gonna get to that, and we're gonna define it right from the bottom. And then finally, we're going to finish off this section by talking about some methods of proofs. So if I make a statement that is either true or false, how is it that I can either prove it to be true or show it to be false, right? So we're gonna talk about some techniques to identify whether a statement is true or to be able to show that this statement is actually a false statement. Okay, so we're going to talk about all of these things, but to start off, we're going to start right from the beginning and let's define what are some basic connectives, what are some basic concepts in logic. So, firstly, whenever we talk about logic, we are working with statements or propositions. Okay, so think of it as we are relating it. This is analogous to statements that we're making in English. And what are statements or what are propositions? They're declarative sentences that are either true or false. That's it. So if you make a statement and that statement is either true or false, it either has a true value or a false value, then that is called a proposition or a statement. Now, any statement that we make, any proposition that we make is going to have a truth value associated with it. So, a truth value of a proposition is either the assigning of true or false to that variable, to that statement. Okay, so let's just give a few examples of propositions. So this should be pretty self-explanatory, but let's start with example 2-1 here. What are some examples of propositions? So first, you might say that I don't know, maybe today is Monday. Okay, so I can say today is Monday. Well, it depends on when you're watching this, but it could be either true or false. So, for example, I can, in that sense, we can assign a variable and we'll call it P that represents the statement today is Monday. So, in this case, if you're watching this video on a Monday, we can say that P has the value true. All right, so we can say P has a value true. Or we can say, if you're watching this video on any other day other than Monday, we can say that P has the value false. Now, just to simplify things a little bit, because later on we're going to refer to this true and false a lot. We're not going to write out the whole term true and false every single time, but typically in this course, what we're going to do is whenever something is true, we assign it a 1, and whenever something is false, we assign it a 0. So 0 or 1 is the value that we're going to give to a proposition. So in this case, we'll say P has the value 1 if you're watching this on a Monday. So we can also have another variable q, and we can also have another proposition, something like aliens exist. Okay, so aliens exist. Is this a proposition? Is this a statement? Well, is it true that it's either true or false? Is this statement either true or false? And the answer is yes, it is it is either true or false. Whether we know the truth value or not is independent. So I might not know whether aliens exist, right? But that doesn't change the fact that this is a declarative sentence that is either true or false. Okay, so it is a proposition. By definition, it is a statement. Okay, so what you see here, these two things, right, these two P and Q, are examples of what we call primitive statements. Okay, these are primitive statements. Now, the definition of a primitive statement is that they are statements in their simplest form. They cannot be broken down into something a little bit more simple. Now, you might be saying, well, what does it mean that it cannot be broken down into something simpler? Well, the contrast of primitive statements is compound statements. So, what compound statements are, they are logical statements that contain a connective. Okay, so anything that contains a connective is what's called a compound statement, and anything that doesn't include a logical connective is called a primitive statement. So, what are compound statements? Or, sorry, what are logical connectives? Well, logical connectives are things like not, and, or, XOR, implication, and biconditional. So you see all of these things are examples of logical operations or logical connectives. So anytime you feel that there's a statement that's being made that contains a logical connectives, then by definition, it is a compound statement. So I'll give you a few examples. I'll give you many examples of this going forward, but just know that P and Q that I've given you here, examples here that I've given you, are examples of primitive statements. Now, while we're on the subject, how do we know that a statement is a proposition? It either is true or false. Well, let me give you a few examples of sentences in English that may not be propositions, that are not propositions. So one example would be a question, like "What time is it?" Right? What time is it? So what time is it is not going to have a value of true or false because there's nothing that we can identify to be true or false. A second thing would be like uh, a command, right? So come over here. Okay, so come over here again doesn't have a true or false value associated with it. Another one would be an opinion. Now, an opinion is a little bit on the gray area. So, an opinion would be like, the weather is hot, right? So, if I say the weather is hot, well, it doesn't really have a true or false value associated with it because hot is not declarative. I don't know what is hot, right? So what might be hot for one person might not be another for might not be hot for another. So anytime we have opinions, again, this is kind of on the gray area. We'll classify it as not being a proposition. However, what I really wanted to tell you at this point is that there is a special type of proposition, which I'm going to call it open proposition for now, which is something like this: X is greater than 3. Okay, so if I have a statement, if I have a sentence that says X is greater than 3, now you might look at this and say, well, this does look like is a statement. It does look like it's a proposition because it does look like it has a true or false value. The only problem is that we don't know what X is. Okay, so here we're assuming that X is a variable, and really we don't know what X is. Is X a number, or is X like a English word? Is X a person? What is X? So as soon as we know what X is, then we can specify whether this is a proposition, or better yet, if what the truth value of this proposition is. So for now, I'm going to say this is close to a proposition, but this is called an open statement. Okay, so for now, we'll label this as an open statement, and later on, we're going to come back and we're going to see what we can do with open statements. Okay, so this is kind of in the future. All right, but let's come back to this logical connectives. What are these logical connectives? So let's go through each one of them, and let's see if we can put some definitions to each one. So the first one is called negation. Okay, so negation is basically the opposite of a proposition. So it takes the opposite truth value of a proposition. So, for example, we would read if P is a proposition, we would read the negation of P as it is not the case that P. It is not the case that P. So it is the negation of P. It is also read as not P. So just a quick way to read that would be not P. And it's denoted with this symbol. So just kind of a dash with the tail at the end, or a negative sign with a tail at the end. And then we have a proposition that goes with it. So again, what is a proposition? It is a statement, is a declarative sentence that is either true or false. Okay, so if P is a sentence that is either true or false, then so is the negation. Okay, so I just want you to take a second to convince yourself of that. So if P has a true or false value, then so does the negation of P. Okay, and in fact, it is the opposite of what it is. So, for example, we can say that if P, so in the previous statement that we had, today is Monday, right? So P, if P is today is Monday, then not P is the statement today is not Monday. Okay, now again, going on the assumption that you are watching this on a Monday, if if P had a true value, then not P would now be assigned false. Okay, so if P is true, then not P is false, and if P was false, then not P would be true. It is the opposite operator for a proposition. Okay, so now, in order for us to define the definitions for a lot of the connectives out there, it is useful to use a truth table. So a truth table is basically giving you a relationship between inputs and outputs, and the inputs could be one or more propositions. You have one or more input propositions, and on the output, you have basically what is the result of this logical connective. So I'll give you an example for negation. So a truth table looks like this. On the left-hand side, typically you will find the input. So what do I need as inputs for the negation? Well, in this case, I only need one variable, right? One variable that can either be true or false. So we'll call it P. And the output, the outcome is not P. Okay, so not P is displaying what is the result of applying the negation to P. So as we said before, if P is false or if P is true, those are the only alternatives for P. So if P is false, then not P is true. And if P is true, then not P is false. So that's it. That is the definition of the negation for this logical connective. Now, just to go back and redefine some of the words that we said before, remember I said that any proposition that contains a logical connective, okay, any proposition that contains a logical connective is going to be a compound proposition. So the question that you have to ask yourself, this statement here, today is not Monday, is this a primitive proposition or is it a compound proposition? Okay, I want you to think about it for 1 second, and you can pause the video for a second if you're not sure. But it is, in fact, a compound proposition. Why? Well, for the easy answer of that, it contains a logical connective. Okay, so anytime you even have a negation, it is called a compound proposition. It is not in its simplest form. So you should just keep note of that. All right, so let's move on. So we have the definition of negation. We also have the definition of the truth table for negation. So what other logical connectives are there? So another one is called a conjunction. The conjunction of two variables, two propositions P and Q, is read as P and Q. And is what goes into the statement. Okay. So once again, if I have P and Q, which are propositions, and what are propositions? the sentences that are either evaluated to true or false, 0 or 1. Then we conjunct these two propositions together and we will get P and Q. It's the statement P and Q. So it is denoted as P, and then this kind of looks like an A, right? But it's kind of like an upward arrow. This is the notation that we're going to use in this course. If you're in other logic courses like philosophy or even a first year computer science course, you may be using different notations. However, I want to specify that in this course, we are using the arrow notation, and it is slightly different. The definitions of each of the symbols are slightly different. So I do want to stick to this symbol that we're using here. So this is read, in short, read as P and Q. Okay, so we have P and Q is the proposition that is true when both P and Q are true and is false otherwise. Okay, now I'm going to come back to this definition. This is actually a very important definition, but let's give a very simple example here. So let's pretend that today is Thursday. We wrote Monday before, but let's say P is today is Thursday, and Q is today's temperature is greater than 10 degrees Celsius. So if we want to identify the conjunction between the two, it is written as P and Q. So if I tell you that today is Thursday and today's temperature is above 10 degrees Celsius, then what does this mean? Logically, what does this mean? Now, again, I want to remind you that all of these logical connectives connect statements, but they do not change the fact that we have propositions. Okay, so it doesn't change the fact that we have propositions. So what do I mean by that? Again, convince yourself that if P and Q are propositions, and I take the and of the two, it will be another proposition, right? So anytime P and Q are propositions, and I say P and Q, that becomes another proposition. So in this case, when I say today is Thursday and the temperature is above 10 degrees Celsius, that's another proposition. Now, the truthfulness, the truth value of this new proposition is going to be dependent on P and Q. Okay, the truthfulness of this new proposition is going to depend on P and Q. So, much like what we did before, we can draw a truth table associated with this. So, we can have P and Q. Now notice that the input side, the inputs on the left-hand side has P and Q. It has two variables associated with it. And what we did earlier with the negation was we identified all of the different values that P and Q, or sorry, the inputs can be. So in this case, there's actually four variations. Okay, so four different variations. Now, again, you can stop the video and see if you can come up with all four variations or all four cases for P and Q, but I'm just gonna draw it here. So P and Q could be 0, 0, it could be 0, 1, it could be 1, 0, and it could be 1, 1. Now, there is a very systematic way of coming up with these variations, but I'm going to tell you later how to do that. Okay, so there's basically four combinations. I should probably say permutations, four permutations of um, values that P and Q should be. Now, think about if you haven't taken a look at our section on counting, you can think about how this comes to be. How is it that two variables is going to give us four different cases, four different permutations? So I'm going to talk about that in 1 second. But for now, let's talk about the definition of and. So we have P and Q. Okay, so we have P and Q, and when is this a true statement? So if I say today is Thursday and today's temperature is above 10 degrees Celsius, when is this true? Well, the answer is the only time it's true is when both P and Q are true. Okay, so when both P and Q are true, this is a true statement. So if today is not Thursday, that whole statement is false, right? So if it's not Thursday, that whole statement is false, right? Today is Thursday and the temperature is above 10 degrees Celsius is a false statement. Similarly, if today's temperature is very hot, it's very cold, it's below 10 degrees Celsius, then also this statement becomes false. Now, of course, in the case where both of them are false, so it's Monday and it's a really cold day on Monday, then it's also going to be a false statement. So ultimately, this what we've drawn here is the definition of a conjunction, the definition truth table for conjunction. So take a look at the definition that we had before. So it is the proposition. So it is in fact a proposition that is true when both P and Q are true. So I'm underlining the key terms here, and false otherwise. Okay, so it's a proposition that is true only when P and Q are true. So only in this case, but in every other case, it is false. Okay, now just convince yourself of that definition and we'll move on. It turns out that conjunction is very much connected to disjunction as well. So what is a disjunction? Well, again, we have two inputs, P and Q. So two inputs, P and Q, they are propositions. It is the statement that is read as P or Q. Okay, so again, it is the statement that is read as P or Q. So this is called the disjunction of P and Q, and it's denoted by a lower pointing arrow, or it kind of looks like a V. Okay, and it is the proposition that is false when both P and Q are false and is true otherwise. Okay, now some of you may be looking at this and saying, this looks familiar. But before we analyze that, let's take a look at disjunction. So disjunction is, well, take the same example as we did before, and the disjunction of P and Q would look something like this. And this statement would be read as P or Q. Okay, P or Q. So P or Q is the case, is true sometimes, and of course false other times. But here again, we have two input values, P and Q. So I'm going to put it into a similar table. And again, we have those four cases for P and Q. So 0, 0, 0, 1, 1, 0, and 1, 1. And again, I will talk about how these cases, how we can come up with these cases quickly. Now, if I say today is Thursday or the temperature is above 10 degrees Celsius, when would this be a true statement? Well, what if it's not Thursday, but the temperature is above 10 degrees Celsius? Well, I did say or, right? So yes, this is true. Okay. What about if today is Thursday, but it's not above 10 degrees Celsius and it's really cold? Okay, well, that would still be true because again, today is Thursday or the temperature is above 10 degrees. So this is still true. What about in the case of both? Well, in the case of both, it's still a true statement, right? Because again, I'm saying today is Thursday or today's temperature is above 10 degrees. So when would this statement be false? Well, the only time this statement would be false is when both P and Q are false. Now, again, you should, at this point, just convince yourself of that. You can pause the video and just make sure that you understand that if I say today is Thursday or today's temperature is above 10 degrees, that the only time that would be a false statement is when both P and Q are false, right? It's Monday, as well as the temperature is really low, right? So, so if you take a look at this definition, we have that this is a proposition, and again, convince yourself that this is a proposition, right? So if I say P or Q, it's a proposition that is false when both P and Q are false and true otherwise. Okay, now I hope you remember that in the previous slide we said something very similar. The conjunction is true when both P and Q are true and false otherwise. And the disjunction is false when both P and Q are false and true otherwise. So what's the relationship between the two? Well, you can see in the graph, in the truth tables, that they're not the opposites of each other, right? However, there is a very close relationship between these two. So what is the close relationship between these two? I'll talk about it very soon. So I'll come back to that for sure. But for now, I want to talk about another type of or. So when I say P or Q, when I have the statement P or Q, in English, we are typically, well, I don't want to say typically, but sometimes in English, we are not using this type of or. So for example, if I told you, after class, I'm going to go play basketball or I'm going to go swimming. Okay, I'm going to go play basketball or I'm going to go swimming. So this doesn't necessarily mean that I'm going to do both. In fact, it's implicated by what I said that I'm not doing both, right? So I'm playing basketball or I'm going to go swimming, right? So there is something wrong with the final row here, right? So when we have P and Q as 1, P or Q somehow shouldn't be 1. So here's another example. Sorry, I should have made this table a little bit smaller. So let me just very quickly redraw this. Um, Okay, so we had 0, 1, 1, 1. So try to remember these tables as definitions. Now, the second example here is we have what's called an exclusive OR. Now, you'll notice that the symbol that we use for exclusive OR is actually very similar to the symbol that we use for OR, with the exception that we have an underline underneath. And this is called an exclusive OR. So the short way of saying this is P exclusive OR Q. P exclusive OR Q. And this is the case where we are indicating that P or Q, but not both. Okay, so this or means P or Q, but it's not both. So you can probably come up with many examples of this, right? So here's another one. So after class, I'm playing basketball, or after class, I'm playing soccer. So there's an indication here that, or there's an implied logic here that I'm not doing both. So the definition here is very similar to the regular or that we did in the previous example, with the exception that the last case is false. So if they're both true, then it's a false statement. Okay, if it's both true, that's a false statement because that is not what we're talking about. Or another way to translate this, once again, is P or Q, but it's not both. Okay, P or Q, but not both. So just to give you another example, if I had P is I'm a boy, Q is I'm a girl, right? So I'm a boy, sorry, I'm either a boy or a girl, is not indicating that I'm both, right? So again, this would be an example of an exclusive or. So later, when we get a chance to translate English sentences into propositions, and I highly recommend that you take a look at some of the examples in the textbook. Take a look at some of the problems in the textbook. When it comes time to translate the English sentences into their corresponding statements in propositional form, you have to identify whether this is a disjunction or is it an exclusive or? Is it a regular or is it an exclusive or? So this is something that you have to decide. And the question you have to ask is, can these two things be done together? Okay, can these two things be done together? So in the first case, when we have today's Thursday and today's temperature is greater than 10 degrees Celsius, is it possible that these two things be done together? And the answer is yes, they can both be true together, right? Can I be a boy and a girl together? The answer is no. So that would be an exclusive or. So this is something that you need to identify while you're doing the questions. Okay. Now I want to introduce two more, and then we'll move into another video here. So the next logical connective is called an implication. Now, implication is while ors and ands are important, and we're going to spend about a week talking about ands and ors. But I think the more important thing to know about this course is implications. So an implication allows a reasoner, so a person who reasons, to be able to come up with new information. Okay, so while it's good to have statements that are true that involve conjunctions and disjunctions, they're pretty static. Okay, so they don't really allow us to be able to gain more information. So what do I mean by gain more information? Well, take a look at the implication. So again, let P and Q be two propositions that are either true or false. Okay, so they are propositions, and the implication is written as P and then arrow Q. Now, so far we've looked at three logical connectives that involve two variables P and Q, but it doesn't matter what order we put them in, right? So in the case of conjunction, for example, P and Q is the same logic as Q and P. Okay, it's the same logic, and same with disjunction, and same with exclusive or. So here is the first example that we see that the order actually does matter. So P pointing at Q, there's a specific name for each one of these statements. So P is called the premise typically, and Q is typically called the conclusion. In fact, those are the names that I'm going to call it from now on. So what P arrow Q is indicating is a couple of things. There's a couple of ways to read this. We can read it as P implies Q. Okay, so P implies Q. If P then Q. So if P then Q is another common way to say it. P only if Q. P is sufficient for Q. So sufficient is probably a term that you'll talk about in philosophy a lot, right? So sufficient means that there's a forward pointing arrow. Q if P, Q whenever P, and Q is necessary for P. Okay, now notice in the last three, right? It is really talking about an arrow that is going backwards. So whenever you say you hear a statement that is Q if P or Q whenever P, then you can guess that these are statements that involve an arrow pointing backwards. Okay, or P is necessary for P. Q is necessary for P. Okay, so ultimately, what does this mean? Okay, so in English, it means that whenever you have a P arrow Q, that the truthfulness of P guarantees Q. Okay, so I'll say that again. P guarantees Q. Okay, so if P is true, that is going to guarantee that Q is true. Now, here's an example that I'm writing here that is a true statement. Okay, so we have a true statement here. Now, are implications always true statements? No, they're not. But just to show you that one way that we can use this in a sentence is that I can say that if I'm greater than 6 feet tall, then I'm greater than 5 feet tall. Okay, so if I'm greater than 6 feet tall, then I'm greater than 5 feet tall. So is it a guarantee? So if P is true, does that guarantee Q to be true? Yes, that's a guarantee. So let's take a look at each one of these scenarios and see what the result is for P implies Q. Now, remember, P implies Q here is a statement. Okay, so it is a statement, and a statement is true unless it can be proven to be false. Okay, so unless it can be proven to be false. So let's start with an easy one. Let's start with the last case here. So if P is true and Q is true, that means I have someone who is greater than 6 feet and is greater than 5 feet. Okay, now does this person disprove the law? Okay, so the rule is that if I'm greater than 6 feet, then I'm greater than 5 feet. That's the rule. Does a person being taller than 6 feet and taller than 5 feet disprove this rule? And the answer is no, it doesn't. So this rule is true. This rule in this case is still true. Now let's jump all the way up to the top. Let's say I have a person who is not greater than 6 feet and not greater than 5 feet. Now, in the context of this rule, does this person disprove the rule? And again, the answer is no, because just because I have somebody who is 4 feet tall, right? They're not greater than 6 feet and they're not greater than 5 feet. That does not disprove this rule, right? So this implication is still true, even though I don't have such a, that even though this person doesn't qualify for either case. Okay. Now, what about the second case? The second case, does it disprove this rule? Now, I have a person that is not greater than 6 feet, but they are greater than 5 feet. So again, we should ask ourselves, can this happen? Right? So let's say this person is 5.5 feet. So if this person is 5.5 feet, then they are not greater than 6 feet, but they are greater than 5 feet. But it still does not disprove this rule. So this rule is still good. This implication is still good. Now you might be saying, how come I keep saying that this implication is still good? Because there is only one way to disprove this rule. There's only one way to disprove this implication. And that is if I'm somehow able to find a person who is greater than 6 feet tall, but not greater than 5 feet tall. So if I'm able to find this person, okay, so the person is greater than 6 feet, but is not greater than 5 feet, then this implication is now false. And this is the only way that we can falsify an implication. Okay? Again, this is the only way that we can falsify an implication. So you might be saying, well, wait a minute. Why is it that the first two cases did not falsify this implication? Well, the answer is that the falsification of a rule, the falsification of an implication, it requires the first case to be true and the last case to be false. Just remember this as a general rule. If I want an implication to be false, the only way to do that is the P has to be true and the Q has to be false. Okay, this is something that we just have to remember, and we'll see this many times in this course. But maybe I'll give you a new example just to see if you can see this example a little bit better. I think one of the problems that we're having, if this is still kind of not making sense to you, is because we know that in this case P implies Q is true. We know it's true. Okay. Now let's pretend that I have a rule about myself and that every Monday I go to SFU. Okay. So if today is Monday, then I go to SFU. I go to my office at SFU. Okay. So I'm going to have a P that says today is Monday and a Q that says today I'm in my office. Okay. So now this is a rule, right? This is an implication. So if I say today is Monday implies that I'm in my office, that means when P is true, then Q is guaranteed to be true. Okay. So let's take a look at each one of the cases again. So if it today is Monday and I'm in my office, then surely this rule is still good, right? It still applies. Okay. But what if it's not Monday today? Did I say anything about me being in my office? And think about it. The answer is no, I didn't, right? The only thing you know is that on Monday, I'm in my office, right? So again, you take a look at these two cases. These two cases are both the case where it's not Monday today. So could I be in the office? Yeah, but I could also not be in the office. So in both of these cases, this implication has not been falsified. Okay, so again, think about this. In the case where it is not Monday, I did not tell you in the statement whether I'll be in my office or not. Okay, so I cannot use these two cases to falsify the claim that today is Monday implies that I'm in my office. So another way to say that is you can't come to me on Tuesday and say, I waited for you the whole day, and well, how come you weren't in your office? Right? Because the only thing that you know is Monday, I'm in my office. Okay, how can I falsify this statement? Well, I can falsify this statement when it is Monday. So this is a one, but I'm not in my office. Okay. So if there is a Monday that you sat there the whole day and I never showed up in my office, then you can say that rule is false. That implication was false, right? So today was Monday, but then you're not in your office. Okay. So notice that this is the only case that this implication can be falsified. Okay, now it does take a little bit to think about, so try to run through this example in your head one more time, just to get the idea of implication. All right, the last one that I want to talk about is the biconditional. So the last logical connective is biconditional. Biconditional looks like this. So it's P and then double arrow Q. Now, I want to go back 1 second and very quickly talk about the implication. So earlier, I gave you the example that I'm greater than 6 feet tall implies, so arrow, that I'm greater than 5 feet tall. Does the implication go the other way? So if I'm greater than 5 feet tall, does it imply that I'm greater than 6 feet tall? Now, obviously, no, it doesn't, right? So there is no guarantee going the other way. So in this situation, we have a one directional implication. One directional implication. So that means Q does not also imply P. but you can probably guess from this notation that P and Q, if they both imply each other, then this is called a biconditional. And again, we have two variables, P and Q here. And P and Q, again, has our four cases. So what is the definition of biconditional? Well, in short, it's that the biconditional can be expanded to the form P implies Q and Q implies P. So when P guarantees Q and Q guarantees P. Okay, so if P then Q and if Q then P. So there's a double implication there, which is not true about the last example that we did. Okay, so what does that look like? Well, it looks like when the truth values, when the truth values are equal, then the biconditional is true, but they're if not equal, then the biconditional is false. Now, you might look at this and say, this looks a lot like the truth table for the exclusive OR. And in fact, it is very similar to the truth table for the exclusive OR, except it is the opposite. It is the negation of the exclusive OR. So perhaps we can write it in another way, right? We can say that the P biconditional Q is equivalent to this and equivalent to this. Now, what does it mean to be equivalent? I'll talk about that later in our next video. But for now, just take this as a note. So we can know that P biconditional Q, the two arrows, biconditional Q, is the same as saying P implies Q and Q implies P. It's also the same as saying it is not the case that P exclusive or Q. Okay, so both, all of those are basically saying logically the same thing. So, so finally, what does biconditional actually mean? Well, in short, it means that they are definitions of each other. P and Q are definitions of each other. So as an example, this is another true statement that you're seeing here. P, I'm a woman with a child, and Q, I'm a mother. Or maybe I should say a woman who's given birth to a child, something like that. And I'm a mother. So these are definitions of each other. So we can check, is it true that P implies Q? If I'm a woman who's had a child, then I'm a mother. Yes, I think that's true. And if I'm a mother, then I'm a woman who's given birth to a child. And the answer is yes. They both imply each other. So they are definitions of each other. So in this case, we would use something like a biconditional. So ways that we can read biconditional is if and only if. So you may have noticed this wording in a lot of math textbooks, especially if we're doing some kind of proof, right? So this, if and only if this, and we're going to come back to this a lot when we do proofs a little bit later in the course. So if and only if is a way to express the biconditional. If P then Q, and conversely. So that's another way that we can express biconditional. And P is necessary and sufficient for Q. So again, necessary and sufficient. This is more of a philosophical term, right? So you might see that in a philosophy course. Okay, so right now we've talked about basically 4.5 types. We'll call it 5 types of logical connectives. We have the negation, we have the conjunction, we have we have the two disjunctions. Sorry, we have the two ors, the disjunction as well as the exclusive or. We have the biconditional, and also we have the implication. Okay, so at this point, what I want you to do is make sure, go back and take a look at the examples that we've created for logical connectives. Make sure you understand what each logical connective means before we move on, because the next step is going to require us to know what these connectives are. Okay, so when we come back, we will do a little bit of a English translation using these logical connectives.